Welcome back to Aerospace Crash Course. Back in episode 2, we talked about the concept of stability, how that meant that if the aircraft's nose pitches up for some reason, we want it to correct itself without any pilot input. We called that stability. But at that point, we left it there and we didn't really explain how to make that happen. Let's get started looking at that right now. This video is turning out to be much longer than I had hoped, and so I'm going to split it into a two-parter. This is part one. We're going to lay some more foundation, and then we'll actually talk about making the stability in the next episode. There will be some math in today's episode, but I have worked very hard to keep that to a bare minimum. I will be showing a little bit of calculus, just a bit, but you don't have to understand that at all. It will not slow you down if you just ignore those parts and move forward. All we really need to do all of this is algebra. We will be doing a lot of algebra though. In the previous slides, all I showed was the lift from the main wing and the weight, and I said that those should be balanced, although I did deliberately leave them a little bit off center like this to maybe spark some thoughts about what would be coming in this video, where we introduce the tail. And in fact, the way I've drawn this diagram, I'm giving the game away just a little bit. So let's look at the influence of the tail a little bit, and then we'll get into stability. Let's do a little bit of very rudimentary background information here. If you're an engineering student or an engineering professor, and I know some of you are, this is very, very basic. But for maybe the casual YouTube crowd, there might be somebody out there who could use this refresher. I'm going to use this symbol right here to represent the CG, the center of mass. I'll say that stands for the center of mass. If we take all the various mass bits that are in this object and we average them all out, they'll land, the center of it will land right at the CG here. I've got a little ruler. And I am finding, I'm dropping it, I'm finding the CG. There you go, I got it. So there you go. The CG is where you can support the object and it will stay balanced. So if you apply any force anywhere on the thing other than the CG, if I apply a force to the CG, it stays level. Anywhere else, it will tip. Okay? So that's what the CG is. And we can say that the entire weight of the object is hanging from that point, the CG. Let's bring in the aircraft. The bar that I've drawn is, sometimes I'm going to use that to represent the whole aircraft for simplicity to clean up my diagrams. But for now, let's keep the aircraft. The main forces we're talking about is the lift from the main wing, and the tail in the back is going to generate some lift. So when I first encountered this topic, when I was learning about aircraft myself as a student, my intuition told me that a diagram like the one I've drawn here would be, would be pretty much how it would work. That the total lift from the wing and the tail together, that together would balance out the weight. And also, presumably, we'd have to have the wing in the front, and then the tail is in the back, of course, and we would have to balance them just right so that they don't cause the thing to go spinning around, right? Okay, so what we're going to look at next is how to do that balancing act. Let's remind ourselves, there's the lift equation again, our old friend, the lift equation, same as before. I want to make a slight simplification to this. We are not going to be varying the air density or the airspeed in today's discussion. So let's just simplify those. I'm going to combine this whole term, 1/2 rho v squared, and I'm going to give it the simplified letter Q. I'm just going to call it Q from now on. That stands for, it's Q for dynamic pressure, of course. If you've ever been watching the rocket launches lately, they often talk about max Q. The rocket is going through max Q right now. And now maybe you can see what they're talking about. They're talking about as the rocket goes up, the density drops, simultaneously the velocity goes up, right? So the dropping density and the increasing velocity are fighting out to see, you know, who's going to win as the Q varies. And so as that rocket goes up, the velocity is increasing, and that's causing Q to go up, but rho is dropping, and that's causing Q to go down. And so, yeah, okay, so that's rockets. Maybe we'll get to rockets someday. But for us, I just want to use that to just simplify my equation. All right, what do I want to do next? I want to pitch the nose of this aircraft up so that we can talk about how the lift is affected by the angle of attack. So I pitched it up, and if you remember our old friend this curve, this data from the wind tunnel talked about how the airfoil would generate lift depending on what the angle of attack was. And I think we can see that now that we've pitched it up, we're going to get more lift. We're going to get more lift on the wing, and I'm just imagining that I've designed my aircraft using this airfoil right here, and I'm going to use it for the tail, and I'm going to use it for the wing. This is a simplified demo, and so we're just using this as an example. So the question here is, in what way does the lift vary with alpha? We're going to want to take the CL, which currently is just a number we're reading out of a chart, and we're going to want to turn that into some math so that we can replace this with an equation. And so I'm going to look at this data, and I'm going to say this data is a straight line. And I think we can agree in this region here, a straight line is a good approximation of that data. So to turn that into a line, I'm going to need the slope of the line. Now, one of the many simplifications that I've made here is I've chosen a symmetrical airfoil. And the symmetrical airfoil has a zero lift at zero angle of attack. That's those data points right there. That just means it's symmetrical, so it's the same up and down. So if you just put it straight into the flow, it doesn't generate any lift. So based on that, if you're looking for y equals mx plus b for the line equation, the familiar line equation from your algebra class, the b is the intercept. That'll be 0. So we just need the slope. Don't look at that. There's a little calculus on the screen. You don't have to look at that. Don't have to worry about it. What we're going to do is rename that with a little engineering shortcut. We will use the symbol C sub L sub alpha to represent the slope of the line right here, the slope of the CL versus alpha curve. We will use this symbol right here for that slope. So if you remember y equals mx plus b, m was the slope, we will put our slope into this now. This is an equation for how we can describe this line. So this is a constant now. CL sub alpha is a constant based on this data right here, and that makes CL can vary as you vary the angle of attack. So let's substitute in CL for what we are going to use here. We'll just bang pop that right in there. So it's now CL alpha alpha, and we have our Q and the SREF. Now, previously, I had just said that the area was a reference area, and I didn't get into what it was. I'm still not really going to get into it much. It's not that important. It is an area that represents how big the wing is. We will use the wing, the main wing, as our reference area. And so depending on how big the wing is, we will put that in there. And we need that because we're going to have lift now on the tail as well. And I think the area of the tail is not the same as the area of the wing. And one of the main points is that the wing is big and the tail is small. So we'll need to reflect that, and we'll reflect it simply by saying that the area of the tail is a different quantity than the area of the wing. And so now we have our equations for the lift of the wing and the lift of the tail based on the angle of attack of the aircraft. Details. there are some details that I've blown off. Some of them are very small little details, and some of them are actually kind of big details. One of those details that I'm blowing off that I want to comment on is I've assumed that the angle of attack of the tail is the same as the angle of attack of the wing here, and that's a stretch. Not even getting into the downwash effect. I'm just blowing off the downwash effect for this audience, but we'll come back to this and we'll see that actually it will probably not be the same. We have the ability to mount our wings at whatever angle we want, right? We can mount the wing pitched up a little bit so that the pilot can fly straight and the wing will still have an angle of attack. And we can mount the tail up if we want extra lift off the tail, or we can mount the tail down, hint, hint, if we want less lift off the tail. But for this beginner's introduction to how we're going to do stability, let's assume that it's nice and straight and symmetrical, and that's the same airfoil for both. We're going to be talking about balancing this aircraft. I mentioned that we want it to be balanced, and if we put all of the weight at the CG, it will be balanced. But we're also going to have lift acting on the tail, and in a moment we're going to see lift back on the wing here again, and we need to keep those balanced. How do we balance those, physically speaking or mathematically speaking? We're going to balance them by zeroing out the torque, or another word for torque is moment of force. And in aircraft engineering terms, we usually use the abbreviation, the letter M for this, and that stands for moment. So I'm going to stick mostly with moment, but if you're more familiar with the word torque, it's the same thing. So just to make the diagram a little easier to read, let's bring in our bar to represent, the bar represents a rigid, fixed rigid thing in space that represents the aircraft, right? So the mass is going to act at the CG, and then we'll apply forces to the bar and ditch the aircraft. Okay, so here we have the tail, and the question is, what is the moment created by that lift force? Well, you may remember, and if not, here's a refresher. The moment of force is the amount of the force multiplied times the moment arm, or the perpendicular distance. So we will locate the tail some distance d sub t away from the CG. And we'll say that the tail's force acts there. So therefore, the moment will be dt times t. Now, we can see from this diagram, the way I've drawn it, this is going to be a counterclockwise force. This torque, I should say, or moment. The moment from the tail is counterclockwise because the tail's lifting here in the back behind the CG. And also, I ditched the plane, but the plane's nose was over here on this side. So this is a nose down torque. By aircraft convention, the pitching moment is considered positive nose up. So this is a nose down torque, and therefore we're going to put a minus sign to indicate nose down. This is not nose up. This is the opposite of nose up. It's nose down. So there's the torque or moment from the tail. So let's bring in the wing. Here's the lift from the main wing. It is also offset by some distance from the CG. So it's going to create a moment. And this one, as I've drawn it here, is going to create a clockwise torque, which is nose up. So that is positive. To begin with, let's talk about what's going on in level flight. In level flight, there's no rotation happening. There's no rotational acceleration happening. And that means no net torque, zero net moment. So that means if we add the moments together, all the moments acting on the aircraft should sum to zero, because that's how you achieve zero rotational acceleration. So we'll just plug in what those are, and I've gone ahead and put the t on the opposite side, remembering that minus sign. So this is what we get. And you'll recall a few slides ago we did this. with our lift and our tails up force here. And so now I can plug those in and get this equation right here. Just a quick costume change, and now let's see if we can reduce this equation a little bit. The CL alphas will cancel, that's on both sides of the equation, as is the alpha and the Q. So those will cancel out, and we are just left with this very simple relationship that lets us describe how we want to arrange the tail and the wing with their sizes and their distances to keep us nice and balanced. And just for simplicity, let's put this in terms of that DL, which is the distance from the wing to the CG. So what we have is that equation right there. With that, I'd like to pause things right here. Let's summarize what we've learned so far, and then we can return in the next video to pick up where we left off. So far, we emphasize that we do have a tail on this aircraft, and so any lift generated by that tail should be added to the lift from the wing, and that's what's compensating for the weight of the aircraft. After that, we reviewed that lift curve that we got from the wind tunnel data, and we showed that it was a straight line, at least in the region that we're going to be working. We gave the slope of that straight line the name CL alpha. And that stands for how does the lift coefficient, CL, vary with alpha. Next up, we talked about the moment and the torque. And in order to keep the thing nice and level and balanced, we're going to need zero total moment or zero torque on it. And that means the torque from the wing and the torque from the tail have to cancel each other out. And then we made quite a few assumptions and some simplifications, and then simplified it down to this relationship that ought to be able to balance the aircraft so that it doesn't spin, which would be a good thing. However, quick spoiler alert, one of those assumptions that we've made, we're going to need to break. That's not going to work. We've made a whole lot of simplifications that are good enough, for, I think, for today's discussion. But one of those things we are going to have to go for and go forward and improve this rather simplistic design in order to achieve our goals. But that's in the next video. In that next video, we're going to take everything that we've got here and move it forward to look at how to achieve that stability that we're looking for. See you over there.